In this lecture, we're going to talk about how do we incorporate lights into the scene. So essentially, how do we do shading? So the main aims are first to understand why shading, what does it do to improve the appearance of objects. So next we will talk about the rendering equation. Then we will discuss different light sources and material types. And then I will introduce the Phong model, which is a very simple reflection model that we'll use for all our lighting calculations. I have slides for something called the modified Phong model. This is no longer much relevant, so I will not talk about it in this lecture, but you can look at the slides if you want. And finally, we will talk about how to compute the different vectors that appear in the Phong model. The reading for this lecture is from Angel, chapter 5. Let's start by answering the question why. Why shading? Why lighting? So far, we have tried to incorporate color in a simple way. So essentially set the color of a vertex, for example, red here. And if we draw a collection of vertices and triangles that form a sphere with red color, this is the kind of picture that we will get. However, what we want is something that looks like this and not the disk that you see on the top. So the real question is, why does the image of the sphere look like this and not like a disk? The reason is that light interacts with the object at different points differently based on several considerations. What are they? The light source, its location, and so on. The properties of the material. Is this a shiny ball? Is this a dull ball made of some material that does not reflect light as much? Where is the viewer located? What is the orientation of the surface? The geometry of the surface? And so on. So the reason these different entities that we saw earlier play a role is that light scatters when it hits surfaces. So for example, consider two surfaces here, A and B, and a light source. Light strikes A, and after it hits A, some of that light is absorbed by the object A, and some of the light is scattered, as you can see. Some of this scattered light goes and hits B, which in turn scatters the light and absorbs part of it. Some of the light that has scattered back from B could come and strike A again, and so on. So you can see that this is a infinite sequence of scattering where the intensity of the light keeps reducing over subsequent scatterings. So this procedure is what produces the final effect that we see. Let's try to mathematically model this process. This is called the rendering equation. So the rendering equation gives us an expression for I, the intensity of light passing from x prime to x. So x is the point that we care about. So let's say this is the light at a particular pixel, and we want to find out how much of this light comes from a particular point x prime. How do we calculate this? So first we have function g, which tells us if x is visible from x prime. And then we have a term epsilon, which tells us how much of the light that emanates or originates from x prime reaches x. The next term is an integral term. And so what we are integrating here is rho, which is the scattering term. So rho captures the amount of light that begins from x prime, reaches x via x double prime. Right? Hopefully that's clear. So, as I said, I captures the intensity of light coming from x prime towards x. Now, if you integrate this over all points x prime in your scene, you get the intensity at a particular point x. As easy as the equation may be, it's kind of clear that we cannot evaluate this analytically, simply because there are an infinite number of rays, in addition to the infinite amount of scattering that happens to these rays. So like I said, the rendering equation describes an infinite scattering. It is a global equation, however, so it does capture all the scattering between objects, which means that it can capture all the real effects like shadows, transparency, and so on. So in fact, ray tracing, you may have heard of this term, is a very special, it's a special case where what we care about is perfect reflecting surfaces. So here is an image, it's ray traced. You can see that there are all the nice 3D effects, but it looks surreal. In reality, you don't have only reflecting surfaces, perfect reflecting surfaces. We have reflecting surfaces of various degrees. Again, to reiterate, the rendering equation cannot be solved analytically. However, we do want global effects, and the rendering equation does allow you to incorporate all the global effects naturally. For example, you can get shadows, you can get multiple reflections, translucent surfaces. All of these in your scene can be modeled and rendered. So in reality, of course, we would like to perform what is called local lighting, where we light an object or a particular vertex without considering the other objects in the scene. So towards that, let's talk about the different elements in the scene and how they can be modeled in order to compute the light at every point, or the shade at every point. Let's talk about light sources first. So general light sources are area light sources. For example, this bulb. These are difficult to work with because essentially you have to integrate all the light coming from the various points on the light source. So what you see here is just 2 points from the light source, but there are an infinite number of such points. In practice, we model simple light sources. More specifically, we model what's called a point source. We model a point source by specifying its position and color. We often talk about something called a distant light source, which is infinitely far away. What this just means is that the light rays coming from this source are all parallel to each other. we often incorporate a spotlight in the scene. A spotlight is essentially a point light source where the light rays are restricted to within a cone. We also incorporate something called an ambient light. An ambient light is like a catch-all component. So the idea is that you cannot model all the lights in your scene. So you give all points in the scene some default background light. This is called the ambient light. So this ambient light aggregates the contribution of all the sources that are possibly present in your scene and all the reflecting surfaces and so on. Next, let's talk about surfaces and surface types. The first surface naturally is a mirror, the perfect reflector. So when a light ray hits a mirror, it gets reflected in exactly one direction, no scattering. A smooth surface is not a perfect mirror. So we talk about smoothness of a surface. The smoother a surface, the more the reflected light is concentrated in the direction of the perfect reflecting direction. In contrast, a rough surface is one that scatters light in all directions. In fact, a perfect rough surface is what we will talk about. The Phong model is a very simple model. The main idea is that it can be computed rapidly. It has three components: a specular component that considers perfect reflectors, a diffuse component, and an ambient component. It uses four vectors: the source vector, the vector pointing towards the source, the vector pointing towards the viewer, the normal vector, and the vector R, which corresponds to perfect reflecting direction. Source here is represented as L, the light source. Let's talk about the ideal reflector, the mirror. So given a point on the mirror or an ideal reflector, we can talk about the normal. This is essentially given by the local orientation of the surface. Given the normal, we know that the angle of incidence equals the angle of reflection. As you can see in this picture, theta sub I equals theta sub R. So if you know this, and we know that the three vectors are coplanar, in addition, if we assume that they are unit vectors, so in particular if we assume that L and N are unit vectors, then we can write an expression for R in terms of L, N and theta. So you can try to derive this on your own, not too difficult. Let's jump to so-called rough surfaces. Now that you have looked at smooth surfaces, let's just jump and look at rough surfaces. And here I want to look at the perfect rough surface. What does that mean? So this is a perfect diffuse reflector which scatters light in all directions, but equally in all directions. The amount of light that it reflects in all these directions is proportional to the vertical component of the light. So cosine of theta, where theta is the angle formed between the light and the direction to the light source. Let me say that again. So theta is the angle between the normal and the direction to the light source. So the reflected light is proportional to cosine of theta. Of course, the reflected light depends on the type of surface. So we model that by specifying a reflection coefficient K sub D that captures the fraction of the light that is reflected. Okay, so now let's talk about imperfect surfaces. So initially we talked about perfect reflectors. Let's talk about specular surfaces, which are not perfect reflectors but close enough. So a shiny surface or a specular surface will display an artifact which is called the specular highlight. So essentially a small dot or a large white region that really shows you how the light is reflected off that shiny surface. So the incoming light is reflected in these various directions, and the shinier a surface, the more concentrated these reflected rays are. This is what we saw earlier, right? So if I try to model that, so phi is the angle between the viewer and the reflected ray, the ideal reflected ray, R. So what we are saying is that the intensity of the reflected ray, I sub R, depends on the coefficient corresponding to the material, K, I, the incoming intensity of light, and cosine of phi. So if phi is 0, then V is in the direction of R, we get maximum intensity, then the intensity falls off as we go away from R. So you can imagine that for a mirror, this falls off immediately. So the only reflected light is along R. If you notice, we had an exponent term there called alpha. So we had the cosine of phi raised to the alpha. This alpha, called the shininess coefficient, captures how shiny the object is. So for alpha equal to 1, you have like a smooth drop off, and as alpha increases, cosine of phi to the alpha becomes more and more pronounced at 0 and looks more and more like a mirror. So values of alpha between 100 and 200, for example, correspond to highly shiny objects such as metals, and lower values are for more dull objects. So the next component is ambient light. Like I mentioned, this is the result of all interactions that we could not model explicitly. The intensity and color really depends on the objects and the lights that are in the scene. The way we incorporate this component is via another coefficient K, just to be consistent with the specular and the diffuse components. So we call it K sub A, and I sub A is the intensity of the light. So in addition to these three terms, we also talk about a distance term. So this is just based on a simple model that says that the light from a point source drops off, the intensity of the light from a point source drops off in a manner that's inversely proportional to the square of the distance. So to incorporate this, we add a factor 1 over a plus bt plus cd square, where d is the distance from the source. A, b and c are some constants that we can tweak or tune to fit the kind of drop-off that we need. So we incorporate a constant and a linear term just to soften the effect of the drop-off. Otherwise, the light drops off, the light intensity drops off quite rapidly, and that can be distracting. So putting all together in the Phong model, we simply add the results that we get from all light sources. So every light source has a diffuse, specular and ambient term, and we simply add them up. This is not physically justified really. It just allows for a lot of flexibility in the computation. So the flexibility also extends to the different color components. So we write different equations for the 3 components of color, R, G and P. So essentially we have 9 components for every light source. So for example here, IDR refers to the intensity of the light, diffuse light, D, in the R component, red component, and so on. Similarly, we model light also using, similarly we model the material properties also using 9 coefficients. So here K sub D corresponds to the diffuse component and G corresponding to green. In addition, we have the shininess coefficient, remember, alpha. Putting all these terms together, for every light source and for each color component, we have the following expression for light intensity I. So we have the first term, which is the diffuse component, K sub D, I sub D. Remember that it is proportional to the angle between the light and normal. And then the specular component, K sub S, I sub S, which is proportional to the angle between the viewer and the perfect reflected ray. And then the ambient component. So the idea is to compute the light at every vertex. So let's say P is a vertex here. The idea is to compute the light at every vertex by computing this expression at that vertex. So you know how to compute these vectors. This is simple computation. We assume that the coefficients are given to us, and then you can compute the light at every vertex. So for the teapot, if you vary the parameters for the material, this is essentially what you get. I think here the light source is fixed. I think it's white light, and the position of the light is also fixed. So only the properties of the material that is changed. So the K properties are changed. So quickly talking about how we compute the different vectors. We specify the light position in your application program, and the camera location and orientation is also specified in the application program, as we have seen in the previous class. So L and V are specified by the application. And we already saw that we can compute R from L and N. But how do we calculate N? Let's talk about that. There is something called the halfway vector that you may have to compute if you use something called the modified Phong model. Like I said, the discussion about the halfway vector and the modified Phong model is in the slides, but I won't talk about it here. Simply because it's no longer relevant now that we have vertex and fragment shaders. So how do you compute N? This is the only thing we didn't talk about. This is essentially just from essentially geometry. So it depends on the surfaces that you are trying to model. If it's a simple surface like a triangle or a planar surface, then you can compute it via cross products. If it is for higher order surfaces like quadrics and so on, then you need to apply more sophisticated techniques. It also depends on how you represent the surface. So note that the light computation is heavily dependent on vectors, and the light calculation happens within the vertex processing stage of the graphics pipeline. So the lights are geometric objects, and their positions are surely affected by your model matrix, the model view matrix. So you need to be careful about when you specify the light source. So depending on when you perform your lighting calculations in the vertex shader, so remember we are doing many things in the vertex shader. So depending on when you perform the lighting calculation, whether you perform it right at the beginning or at the end, you would be moving the light source with the object, or you would be fixing the object and moving the light source, or you would be fixing the light source and moving the object, or you would be moving them independently. So you need to be careful about this. Again, some rules of thumb may be followed here. So finally, I want to discuss two types of shading. Now that we are using shaders, this discussion becomes quite relevant. Gouraud shading is what we often would do in computer graphics for a long time. So Gouraud shading works as follows. You find the normal at every vertex. You apply the Phong model at each vertex. So we have already seen the expression for the Phong lighting model. So this will give you the light intensity or the color at every vertex. And these colors are interpolated as the triangle gets converted into a collection of fragments. So in Gouraud shading, what you interpolate is the vertex colors or the vertex shades. But what you compute is essentially the normals. So if you have a vertex such as this, and you have multiple edges going out from that vertex, let's say there are triangles between all of them. Each triangle can be used to compute a normal, and the normal at this particular vertex can be calculated as an average of the normals of all the triangles that are incident on the vertex. That gives you your normal at that vertex. So this is what I mean by an average normal. Now you can compute the normal in any way that you wish. Right. So let's next talk about Phong shading. In Phong shading, you again find the vertex normals, no difference here. But now you interpolate the normals across the edges and the polygons, if in case you use polygons to represent your object. And then what you do is you find the shades along the edges and inside the polygons by computing the Phong model within each point inside the edge and inside the polygon. So let's talk about the two shading techniques in a little bit more detail. So with Gouraud shading, the quality really depends on the number of primitives that you have, or more specifically, it depends on how many pixels does that primitive project onto, right? So here are two examples that illustrate this idea. On the left, you have a sphere modeled using a large number of triangles. On the right, you have the same sphere modeled using fewer number of triangles. So each triangle on the left maps to fewer number of pixels. So Gouraud shading works well in this case. Whereas on the right, each triangle projects to a large number of triangles. So you actually see the creases more clearly. So for Gouraud shading to work well, you need a large number of triangles or a large number of geometric primitives. Phong shading works by interpolating the normals, not the colors or the intensities. So essentially if you have two vertices, let's say P sub 0 and P sub 1, you have the normals at these two vertices, P sub 0 and P sub 1. So let's call them N sub 0 and N sub 1. You interpolate the normals along the edge connecting P sub 0 and P sub 1. And for each point along the edge, now you have a normal. You recompute the shade using the Phong model. So note that the term may be confusing. We are talking about Phong shading as a method here, but we are using the Phong lighting model, which is common. Okay, going back to interpolating normals, at every point on the edge, we can actually compute the light intensity using Phong shading model because we have access to each of these points from the fragment shader. So in Phong shading, what you do is you postpone the lighting calculations to the fragment shader. In the vertex shader, you simply compute the normals and then you allow the graphics pipeline to interpolate the normals. Within the fragment shader, you can now compute the light at every fragment. A quick comparison. If you have meshes that approximate high curvature surfaces, by high curvature we mean surfaces where the normal changes rapidly, then Phong shading may generate smooth looking images, whereas Gouraud shading will show you edges, especially where the normal is changing rapidly, right? Because you are approximating a large part of that surface using a triangle with a flat shading within that triangle. So essentially you are using the same normal within that entire triangle. On the flip side, Phong shading requires much more work. You have to compute normals at every fragment and do calculations at every fragment. So earlier you didn't have access to the fragments in the hardware. So this was Phong shading was not really feasible. So hence it was not available in many real-time systems. But now, of course, you can write a very simple fragment shader and support Phong shading. However, both Gouraud and Phong shading require data structures that allow you to locate vertices, their neighbors, so that you can compute normal at those vertices. So we need to remember that. Quick discussion on what a typical graphics API should provide for lighting. So OpenGL may not provide all these functionalities, but anyway. So an API should give you the ability to specify light properties, right? What kinds of light, what color, and so on. Properties of materials. So of course, these can be abstract materials that are used by different objects and different polygons or different triangles. Sometimes the material properties also include an emissive component where the material functions like a light source. The API typically provides some support for transparency and blending between different colors. We will actually see this a few weeks later. The API should support color being computed for every vertex and some form of interpolation of color during rasterization. You also want from the API the ability to distinguish between front and back facing surfaces, faces. So this is something unique only for this synthetic camera model and computer graphics. Every polygon or every triangle has a front and a back face. We actually distinguish between these two. We could assign different colors to the front facing triangle and the back facing triangle. So for example, in the cube on the left, you can assign a different color to the front facing, to the outward facing surface and maybe like another color to the inward facing face. So what this means is that when you look at an object which is cut open, like what you see on the right, you will be able to distinguish between the outward facing faces and the inward facing faces. So the default in many APIs or even in OpenGL is that you shade only the front faces. And this works very well for convex objects. So face objects such as what you see on the left. But often you don't have just convex objects in the scene. So you perform what is called two-sided lighting. So where you think of both sides of the polygon or the triangle as two different polygons and do lighting calculations for each one with maybe the same color or different colors. So each side can have its own properties. So in GL, you can look for these different variables, GL front and GL front and back, which allows you to specify how to do the lighting. So with that, we come to an end of this discussion on lighting and shading. We already saw how to compute the color at every vertex. So this is how you incorporate color into your scene.